Hi everyone, I am your friend Shadab Imam and we are continuing our lecture series on operations research. So today we are continuing our lecture on two-phase method, and let us see with an example. Let us see the question. It says that maximize z is equals to 2x1 plus x2 plus 1 by 4 x3 subject to constraints 4x1 plus 6x2 plus 3x3 less than equal to 8. 3x1 minus 6x2 minus 4x3 less than equal to 1, 2x1 plus 3x2 minus 5x3 greater than equal to 4, and x1, x2, x3 greater than equal to 0. Now, as we know that in two-phase method, we will separate the problem into two parts. In the first phase, we will find out the basic feasible solution, and in the second phase, we will try to optimize that particular basic feasible solution. So initially we need to convert this constraint into standard form. So let us convert this into standard form. So it is 4x1 plus 6x2 plus 3x3. This is less than equal to sign, that means we need to add a slack variable here. So s1 will be the slack variable, is equal to 8, and the second constraint 3x1 minus 6x2 minus 4x3. Here also we have less than equal to sign, that means we need to add a slack variable again. So plus s2 equal to 1, and the third constraint is 2x1 plus 3x2 minus 5x3. Here the sign is greater than equal to, so we need to subtract a variable which is surplus variable. So minus s3 is the surplus variable, and we need to add another variable which is artificial variable. So plus a1 will be equal to 4, and we need to make sure that x1, x2, x3, s1, s2, s3 and a1 all are greater than equal to 0. Now in the first phase we need to find out, or we need to make an artificial objective function where we eliminate the artificial variable. So in this particular problem, the first artificial objective function we have will be minimization. Minimize z dash is equals to a1, because there is only one artificial variable. So our objective is to minimize that artificial variable or to make it 0. So in order to solve this problem, we will convert this minimization into maximization. So our problem will convert as maximize z dash is equals to 0x1 plus 0x2 plus 0x3 plus 0s1 plus 0s2 plus 0s3 minus a1. So this plus a1 converted into minus a1. Now let us start solving. So in the first phase, this is the first phase, phase 1. This is phase 1, and in this phase we will write the objective function as x1, x2, x3, s1, s2, s3 and a1 with the artificial objective function coefficient as 0, 0, 0, 0, 0, 0 and minus 1. And we also know that if we put x1 equal to 0, x2 equal to 0, x3 equal to 0 in these three equations, we will get s1 is equals to 8, s2 is equals to 1, and if we put s3 equal to 0, because s3 is not eligible to participate in the basis column, so we will put s3 equal to 0 and we will get a1 equal to 4. So s1, s2 and a1 all three are eligible to enter the basis column. So here s1, s2 and a1 with the objective function coefficient or artificial objective function coefficient as 0, 0 and minus 1. Now let us write the constraints coefficient 4, 6, 3, 1 0 0 0 equals to 8. Similarly 3 minus 6 minus 4 0 1 0 0 equal to 1. Similarly 2 3 minus 5 0 0 minus 1 1 equal to 4. Now let us find out the value of Cj minus Zj. So here all the Cj values are 0 except this. So S1, S2 and A1, all three are basic variable. So we will put the values of Cj minus Zj as 0 for S1, S2 and A1. And now this will be minus 2, 0 minus of minus 2 is plus 2. Similarly 0 minus of minus 3 is plus 3, and this will be minus 5. This will be minus 1, and Z I am not calculating here because artificial variable is appearing in the matrix. So in this portion we know we will consider the maximum positive value in the Cj minus Zj row. So as we can see here that 3 is the maximum positive value here. So this is our key column. That means variable x2 will now enter the basis, and to find out the leaving variable we need to calculate another term, that is minimum replacement ratio theta, which is right hand side value divided by corresponding key column element. So let us calculate this. This is 8 divided by 6, which is equals to 4 by 3. This is 1 divided by minus 6. Here minus sign indicates that this variable is not eligible to participate. So we will put a dash sign here, and this will be 4 divided by 3. 4 divided by 3. So now as we can see here that there is a tie for the leaving variable, and we know that whenever there is a tie for the leaving variable, it is a possible case of degeneracy. And one more thing we know that we can select arbitrary any of the two variables as the outgoing variables. So generally what we do is we will select the artificial variable as the outgoing variable, because this is our objective, that is to eliminate the artificial variable. So generally what we do is we will select this as our pivot row, and we will replace artificial variable A1. But we can also see that when whatever value we will select, it is compulsory that in the next iteration the other variable will have 0 right hand side value, and we know that. So what now we are trying to do is we will select the other variable S1. So if we select S1 as the leaving variable, we know that in the coming iteration the right hand side value of A1, variable A1, will be 0, and with artificial variable with right hand side value 0 is also a basic feasible solution. So we will this time try this, that if we select this variable S1 as the outgoing variable, and then we can have the right hand side value of artificial variable A1 as 0 in the next matrix, and let us see how we can approach through that. So let us consider this as our leaving variable, that means this is our pivot row, and we have selected the variable S1 as our leaving variable. So now the variable x2 will replace S1. So let us write here x2, S2 and A1 with objective function coefficient as 0, 0, minus 1, and the pivot element here is the intersection of key column and the pivot row, which is this element. So we need to make this pivot element as 1 and the remaining element in the column as 0. So what we'll do is we'll divide row 1 by 6 to make this as 1. So So I will divide row 1 by 6. So this will become 2 by 3. This will become 1. This will become 1 by 2. This is 1 by 6. This is 0, 0, 0. This will become 4 by 3. Now, in order to make this element as 0, what I will do is, I will take row 2 plus 6 times of new row 1. Row 2 6 times of new row 1. So by adding this, I will get a 0 here. So this will be 3 plus 6 times of 2 by 3. 6 times of 2 by 3 is 4. 4 plus 3 is 7. So this will be 7. Similarly, 6 minus 6 plus 6 will be 0. Minus 4 plus 6 times of this is 3 plus 3. Minus 4 and plus 3 is minus 1. Minus 4. This is into 6. That means, okay, plus 3. This will be minus 1. Okay. So 0 minus of 6 times is 1. This will be 1. 1 minus 6 times 1 plus 6 times of 0 is 0. 0 plus 0 6 times of 0 is 0. This will also be 0. 1 plus 6 times of this. So 6 times of this will be 8 plus 1 9. So this will be 9. Similarly, I need to make this element as 0. So what I'll do is, I'll take row 3 minus of 3 times new row 1. Row 3 minus of 3 times row new row 1. So 2 minus 3 times of new row 1. So this will be 2 minus 2 is 0. Okay, this will be 3 minus 3 is 0. This will be minus 5 minus 3 by 2. This will be minus 13 by 2. 0 minus 3 by 2. This will be, this is minus 3 times. So this will be minus 1 by 2. This will be 0 minus 3 times of this is 0. This will be minus 1. Similarly, this will be 1. 4 minus 3 times of this, 4 minus 4 will be 0. And so here we can see that, as we have discussed, that by selecting the variable s1 as the leaving variable, we will have the value of other variable, that is artificial variable 0, in the right hand side column. And we know that we will terminate our iteration whenever we eliminate the artificial variable, or the right hand side value of the artificial variable will have a 0 value. So here we can say this is having a 0 value. So first of all, let us calculate the value of Cj minus Zj. So here x2, this will be 1, I guess. Okay, 1. So there is a calculation mistake. 0, 0, because x2, s2 and a1 are basic variables, so they will take value 0 in the Cj minus Zj row, and here we will calculate. This will be 0 minus 0 is 0. Again this will be 0. Again this will be 0, and this will also be 0, and objective function will come as 0, but we'll put a dash sign because it is only phase 1 and we do not need to calculate the value of z here. So as we can see here, that we have finally found our basic feasible solution, and we can accept this basic feasible solution although artificial variable is appearing in the final solution, because the right hand side value of the artificial variable is coming as 0. Now in the phase 2, what we'll do is, we will take this value and we will put it in the starting solution in the phase 2. So let us start solving phase 2, and to solve the phase 2, I am just erasing the top portion here. So I am just erasing this part, and we will solve here, and in this phase 2 we will use the original objective function we had in the question. So let us see what is our original objective function there. So I'll erase this also. Okay. Let this be, this is S2, this is A1. So I'll take this matrix here. So the basic variables are x2, s2 and a1, and the original objective function is this one. And one thing we need to understand here, that once this objective function is used, we can say that we have 0 s1 plus 0 s2 plus 0 s3 plus 0 a1. If we have artificial variable here, then also we will take is as 0 coefficient in the objective function. Okay, this is what we need to remember here. And let us start solving the phase 2. So the objective function will be the original objective function that is given in the question, which is 2, 1, 1 by 4, 0, 0, 0, 0, and these three are the variables in the basis column. So their objective function is 1, 0, 0, and the matrix is 2 by 3, 1, 1 by 2, 1 by 6, 0, 0, 0, equal to 4 by 3. This is 7, 0, minus 1, 1, 1, 0, 0, equal to 9. Similarly, this is 0, 0, minus 13 by 2, minus 1 by 2, 0, minus 1, 1, equal to 0. Okay, so now I am erasing the second portion because I have already noted this down. So let us erase this and start solving the phase 2. So this was the final solution in the phase 1, and we will take this as the starting solution for solving phase 2. And in the phase 2, let us calculate the values of Cj minus Zj, as x2, s2 and a1 are the basic variable. They have the value 0 in the Cj minus Zj row. Now this will be 2 minus of 2 by 3 is 4 by 3, this is 4 by 3, and this will be 1 by 4 minus 1 by 2 is minus 1 by 4, and this is 0 minus 1 by 6, this is minus 1 by 6, this will be 0, and the right hand side value, the value of z is coming as 4 by 3. So this is our first matrix in the second phase, and as we can see here that one of the values is coming as positive. That means we will select this variable as our key column, and it suggests that variable x1 will now enter the basis. And to calculate the leaving variable, we will calculate the value of theta, which is right hand side value divided by corresponding key column element. So 4 by 3 divided by 2 by 3 is 2, 9 divided by 7 is 9 by 7, and as we see 0 divided by 0, whenever we are getting confused what to do when we have both sides 0, then always see what is given in the key column. If in key column it is given negative or 0, that means we will put a dash sign here, and this means that variable a1 is not eligible to participate for the leaving variable. Okay, so now as we will do we will select the minimum positive value among these two as the leaving variable. So as we can see here, 9/7 is the minimum value, so we have to select this value as our leaving variable. But before doing that, we need to consider one thing, that after selecting this particular value, this particular variable as the leaving variable, we must not change the value of this 0. That means the corresponding value of artificial variable in the right hand column is 0, and this should not change to positive. If this was happening, then we will not follow this particular rule. Okay, so I'll tell again what I've said is that after selecting among these two, suppose 9/7 is the minimum positive value, before selecting this value we need to ensure that our right hand side value of artificial variable a, that means this 0, will not change into any positive value. Okay, so let us see how can we make sure that this value will not going to change. We can see this by having row operation, because when we select this variable s2, we will have this as our pivot element. That means we need to make this element as 1 and the remaining two element as 0, and because this element is already 0, we will not do anything in this particular row, and this right hand side value 0 will remain as it is. If there was a positive value here, then only positive or negative value here, then only we have to think or calculate whether this is coming 0 or not. In this case, it is very clear that if we select this s2 as the leaving variable, we have to make this pivot element as 1 and the remaining two element as 0, and this element is already 0. That means we do not need to do any operation on this particular row, and this 0 will remain as it is. So it is clear that we can select this as our outgoing variable. So we have selected variable s2 as our outgoing variable. This is our pivot row, and the intersection of key column and the pivot row is our pivot element. So 7 is our pivot element. Now it is clear that variable x1 will enter the basis and will replace the variable s2. So let us do this. Variable x1 variable x2, variable x1 and variable a1. The coefficient, objective function coefficient are 1, 2 and 0. Now to make this element as 1, I will divide this row by 7. So this will be 1, this will be 0, this is minus 1/7, this is 1/7, this is 1/7, this is 0, 0, and this is 9/7. Okay, now as this is already 0, I will write the equation as it is. That means 0, 0, minus 13/2, minus 1/2, 0, minus 1, 1 and 0. Now in order to make this element as 0, I will do row 1 minus of 2/3 times of new row 2. So 2 minus 2/3 times of this is 0. 1 minus 2/3 times of 0 is 1. 1/2 minus 2/3 times of this is 25/42. This is 25 this will come as 25/42, and 1/6 minus 2/3 times of 1/7, and this will come as 1/14. This is 0 minus 2/3 times of this. That means this is minus 2/21. This will be minus 2/21. 0 minus 2/3 times of 0 is 0. 0 minus 2/3 times of 0 is 0. And 4/3 minus 2/3 times of 9/7. This will come as 10/21. This will come as 10/21. 21. Now as we have calculated this matrix, we will calculate the value of Cj minus Zj to check the optimality, and as we can see that variable x2, x1 and a1 are the basic variables. They will attain the Cj minus Zj value as 0. Now here we can see that this is 25, this is minus 2, so 6, 13. This will come as minus 5 by 84. This will come as minus 5 by 84. For this will be 2 into 2, 4, 5. This will be minus 5 by 14. This will be minus 5 by 14, and this will be minus 2 tenths of this will come as minus 4 by 21, minus 4 by 21, and S3 will come as 0, and the value of Z 10 into 10 by 21 plus 18 by 7, it will come as 64 by 21. This will come as 64 by 21. Now as we can see that all the element in the Cj minus Zj row are either 0 or negative. That means we have obtained our optimal solution, and as we can see that in our optimal matrix we have the artificial variable a1, but because artificial variable a1 contains a value 0, that means the value of a1 is coming as 0. This is why this can be considered as an optimal solution, although the artificial variable a1 is appearing in the final matrix. So here after attaining this solution, we can say that the value of x1 is coming as 9 by 7. The value of x2 is coming as 10 by 21, and the value of x3 is coming as 0 because x3 does not appear in your final solution, and the value of z, that is z max, is coming as 64 by 21. 64 by 21. So this is our answer to the problem, and we can also do it the other way as we have discussed in the phase 1. If we have selected a1 as the outgoing variable and we have solved, then also we will get this solution, but we instead of that we have selected the other variable, so that the value of artificial variable will attain a 0 value. So here I hope this clears the question. So if you like the lecture, please share the lecture. Have a nice day. Thank you.